Figure 1 shows a cell used to measure the standard electrode potential for the half cell Mg2 plus 2 electrons goes to Mg. So you can see we've got this diagram. We've got the hydrogen half cell on the left, the standard hydrogen half cell, and we've got the magnesium half cell on the right. State the purpose of the salt bridge. So the salt bridge is going to allow us to complete the circuit and allow the transfer of ions between the two half cells. So we want to write complete the circuit and allow transfer of ions. So that's how it's completing the circuit. And identify an ionic compound that could be used in this salt bridge. So we want to put in something that won't react with either half cell. So often we say use either KCl or KNO3. I'm not going to pick KCl because that would change the concentration of the chloride ions in the half cells. So I'm going to use KNO3 as my salt bridge containing substance. State how, if at all, the EMF of this cell will change if the surface area of the platinum electrode is increased. Well, change in the surface area has no change on equilibrium, just changes the rate at which we achieve equilibrium. It doesn't change the position and therefore it doesn't affect EMF. The standard electrode potential for the half cell is shown, it's negative. Water is added to the beaker. So our mixture is that we've got on one side the hydrogen half cell, which we know is this half equation, and we know that that has a electrode potential of 0.00 volts, and our other half cell is the magnesium, and that's minus. Water is added to the magnesium chloride solution, so that is going to change the concentration of Mg2+. It's going to reduce the concentration of Mg2+, which means this equilibrium will shift to the left to replace it, and this value here will become more negative. So there will be, if you think about it in terms of the EMF of the cell, what you've got here is you've got something that's 0.00 volts and something that is minus 2.38 volts. And we're shifting the equilibrium left on the magnesium half cell, making it more negative. And so overall, the gap, the distance away from the hydrogen half cell is going to increase. The voltmeter V is replaced by a bulb, and then it says give the overall equation for the cell when the cell is operating. Alright, so remembering that we had the two half cells, and the hydrogen one was more positive, it was 0, but it was bigger than our magnesium one. And so the more positive one gets to go the way it's written, which is gets to behave as a reduction, and our magnesium one needs to be reversed. And then we're going to combine those two. So we can cross out this one because we've reversed it. So we've got Mg plus 2H plus goes to Mg2 plus H2. And we can see that the charges balance and the atoms balance as well.